Hello and thank you for watching my video. My name is Astrid Krasniqi. I'm CCNA and CCNP certified instructor. Today we are going to be covering Chapter 2, LAN Redundancy. This is a part of CCNA Semester 3, Scaling Networks, Chapter 2. On this chapter, objectives for Chapter 2, LAN Redundancy are as follows. First, 2.1, Spanning Tree Concepts. Here we describe the issues with implementing a redundant network. And then we describe the IEEE 802.1d STP operation. Then we move on to section 2.2, varieties of spanning tree protocols. Here we describe the different spanning tree varieties, describe the per VLAN spanning tree plus operation in a switched LAN environment, and then we describe the rapid per VLAN spanning tree plus operation in a switched LAN environment. Then we move on to section 2.3, which is spanning tree configuration. Configure rapid per VLAN spanning tree plus switched LAN environment, and we identify common spanning tree protocol configuration issues. Then last section is 2.4. Here we talk about first hop redundancy protocol. Here we describe the purpose and operation of first hop redundancy protocol. We describe the different varieties of first hop redundancy protocols, and we use the Cisco IOS commands to verify HSRP and GLBP implementation. Section 2.1, Spanning Tree Concepts. First, in this section we talk about what is layer 2 loop. Broadcast and layer 2 loop can be dangerous combination. Layer 2 we mean in OSI layers. Layer 1 physical layer, layer 2 data link layer, and that's it. We are not moving to layer 3, layer 4 and so on. Here we have a layer 2 loops. Layer 2 they are called frames. At layer 3 they called packets. So any data what we talk about in layer 2 is called a frame. A frame could be looping around a network forever without stopping there because we don't have something called TTL or time to live. For example, in IP layer or layer 3, there is time to live. So when that time to live reaches 0, the frame or packet at that layer will be dropped. A layer 2 frame does not have a time to live. So if there's a loop, for example, if it goes in one interface and comes back on a different interface, it's considered a loop, but there's no way to stop that loop. Well, there is protocol like spanning tree which you're going to be learning, but if you don't have a spanning tree, the frame could be looping forever. After the Ethernet frame starts to loop, it would probably continue until someone shuts off one of the switches or breaks a link. So for example, if there is a loop and there's no spanning tree running, the frame will be looping forever until you can shut the switch, or you can just unplug the cable that's connecting the two switches, but there's a loop. IP has a mechanism to prevent a loop, like we said, time to live. Bridge loops can occur at any time there is a redundant path or loop in the bridge network. So as soon as we have a redundant path from one switch to another switch, then we could have a loop there. The switches will flip-flop the MAC addresses, tables entries, creating extremely high CPU utilization. That's called the MAC address instability. So for example, because the frame is looping from one interface to another interface, it's coming once in one interface, the switch is updating the MAC address table, and suddenly it's coming on a different interface, and the switch has to update the MAC address table again. Unicast, unknown unicast, and broadcast are all problems. The purpose of spanning tree protocol is to avoid and eliminate loops in the network by negotiating a loop-free path through a root bridge. Spanning tree protocol determines where there are the loops and block links that are redundant. Ensures that there will be only one active path to every destination. So redundancy on OSI layer 1 and 2, for example, don't forget, these are the hierarchy. We have access layer switches here, then we have a distribution layer switches, and we have a core layer switches. You can see everything is nicely redundant. So if one path fails, then we will start using another path. A layer 2 loop can result in three primary issues. So if we have a loop, then we can have those three problems. The first one is called MAC address database instability. Instability in the content of the MAC address table results from copies of the same frame being received on the different ports of the switch. The second problem that we could face is something called broadcast storm. Without some loop avoidance process, each switch may flood broadcast endlessly. This situation is commonly called a broadcast storm. And the third problem is multiple frame transmission. Multiple copies of unicast frames might be delivered to the destination station. Many protocols accept to receive only a single copy of each transmission, and this can cause some unrecoverable errors. Here I'll set up a slide so trying to address all those three issues: MAC address database instability, broadcast storms, and multiple frame transmission. For example, I want you to imagine that we have a PC, and this PC IP address is 192.168.1.10/24. This is the MAC address AA:BB:CC:11:22and33. So it's represented, remember, MAC address is represented in hexadecimal units. The PC is connected to switch A at port FA06. The switch A MAC address table or MAC address database is empty. Just imagine it's a brand new switch, we just turned it on. The switch A is connected to port 10 and port 11 are connected to switch B at port 20 and 21. Switch B MAC address table is empty as well, it's a brand new switch. And switch B port FA018 is connected to PCB, which IP address is 192.168.1.20, and the MAC address DDEEFF4455 and 66. And imagine that PCA is trying to communicate with PCB. Now, PCA will generate this PDU, or this like all the layers. So we have the PDUs. We are concentrating only on layer 3 and layer 2. So layer 3, for example, the source address is 192.168.1.10, which is itself. Destination address is 192.168.1.20, which is a PCB IP address. And layer 2 source address is AA itself, BB:CC and so on. Layer 2 destination is DDEEFF, which is PCB. Now PCA will send this data to PCB, and as it goes to the destination, so it starts flowing towards switch A. At the switch A is called the frame. Switch A, well, first thing it's going to do is going to look at the source. I abbreviated the source here, AA, so I don't have to write the whole MAC address. And DD is the destination, the first two letters of this MAC address. So it looks at the AA, that's the source address, where it's coming from, or source MAC address. So the first thing the switch A is going to do is going to write down on his, or populate his MAC address table, saying, okay, well, I got the source AA, MAC address, some MAC address AA, at port FA06. It just came in FA06. But the destination of this frame is DD. I'm going to look at my MAC address table and find out if I know where that destination is. And I don't. So if I don't know where the destination of DD is, what I'm going to do, I'm just going to flood this frame. So the switch is going to create a couple of frames extra, not extra, but it's just going to flood it to every port apart from the port it came in. So it came in FA06, so it's not going to send it back there, but it's going to send it 10 and 11. Right? So now imagine that switch B receives the same frame from switch A. Now you can see here, he's going to add it. He's going to say, okay, well, I got the source, same as switch A was doing it. I was going to look at, I got the source AA, and it came in port FA20, so let me update my MAC address table. My MAC address table, I'm going to write it there, port 20, MAC address AA came. But destination is DD, and I don't know where the DD exists. Switch B says that as well. So I'm just going to flood it. I'm going to send it to every port apart from the port they came in. So he creates this two extra frames. One that is going to go to FA021 and one that is going to go to FA018. Right? But just before he sends it, it receives another frame coming from switch A, and this frame again is called, well, the source is AA, but now it's came in FA21. So the switch B, what's going to do is going to remove that, what they had before, the information they had before, and is going to add it to 21. Now, this is called a MAC address instability. So as soon as one frame is coming in one port, and the same frame is coming from a different port, so this switch is going to just swap or flip-flop the MAC address like we were saying earlier on, and this is a MAC address instability. So now it's going to create the two frames again, and it's going to send it. Imagine the red frame already been sent to PCB. So PCB already got that frame, and it's going to get another frame from the blue one. I hope you are keeping up, because if you're not, you can just rewind, go back and look at it again. But this is a dual packets or dual frames that this PC has received, right? So that is a dual or multiple transmission, which is not, some protocols, they don't allow this at all. They don't accept this at all. So this is going to cause some, like we said earlier, unrecoverable condition here on the PCB. So we saw the two problems here, that we saw MAC address instability and we saw multiple transmission, as well as there's a loop here, right? Because now that frame, the red frame, has just came back to PC switch A on the port FA011. So what the switch A is going to do is going to remove from FA06 and it's going to put an FA011. That's a source. But again, it doesn't even know where the destination DD is yet. So it's going to send it back to PCA. Is going to get his own frame back, and it's going to send another one, an FA010. And imagine it's going to come back, another one is going to come back again, the blue one. So the switch A has to delete that from 11 and put it in 10 now. As you can see there, there's a big problem here with the MAC address instability. Right, so very, very quickly, the frame is just going to loop around here, and it's going to use all the CPU resources of switch A and switch B, so they cannot process any more frames. Lucky we have a solution for this, and it's enabled by default, and that's called a spanning tree protocol. But here you are here to learn what spanning trees does and why spanning tree is here. The spanning tree's reason for this is for those three problems: MAC address instability, multiple transmission, and broadcast stall. So redundancy, imagine we have a switch A again, and it's connected with switch B. Now we have one connection. That's not very good setup, because if this cable breaks or ports malfunctions or whatever, then switch A and B cannot communicate with each other. But the PCs are connected to it, they will not be able to communicate with each other. So you add another cable. When we add another cable, here we cause an issue. There's a redundancy, a great redundancy. If one of them breaks, the other one will take over. But there could be a loop. There could be a potential loop here. So we have another, we connect it to another switch, we cause another potential loop here, and we connect another between the switches. So definitely we have a nice redundancy here, but big challenging topology for us to find out if there's a loop. And these are the access layer switches, and we connect them as well. So now really you have, there's a nice redundancy everywhere, but there's got to be a method to stop all these loops. So redundancy at layer 1 and layer 2 is a key to maintain a network reliability, because if one of the cables fails, we always have an alternate path. Multiple physical links between devices provide redundancy. The network can continue to operate with a single link or port has failed. So if one of them fails, the other one will take over. There's a nice redundancy, okay? So if we send it framed this way and this link fails, we can go this way. If both links fails, we can go this way, and so on. We can just use a different redundant path. So redundant links can also share the traffic load and increase capacity. Well, that's even better. So we can share load, or we can share the traffic load. Multiple paths need to be managed so that layer 2 loops are not created. The best paths are chosen, and alternate paths immediately available if the primary path fails. So imagine this is the best path. So this link, we're going to switch from switch B to switch A, or A to B. The top one is best path. This will be shut down. It will be set on the blocking mode. So if the primary path loses, we lose the primary path, the backup path will immediately be available for us. So the spanning tree protocol are used to manage layer 2 redundancy. So spanning tree chooses a reference point called a root bridge. So one of these switches is going to be a root bridge. A root bridge means is a reference point to our network, to our topology. So then determines the available paths to that reference point. If more than 2 paths exist, spanning tree algorithm picks the best path and blocks the rest. So, for example, let me just not go too fast. Example, we take switch A as our root bridge. So all the other paths, we can see we have a nice redundancy here and everything, but the spanning tree algorithm is going to block or remove any redundant paths. So as you can see, spanning tree algorithm, well, this is my design, yeah, but that's what the algorithm will do. It will leave not redundancy. It will block any paths and it will keep only a single path to every destination. So as you can see now, there's no redundancy, there's no loops. A port is considered blocked when user data is prevented from entering or leaving that port. So as you can see, all the ports now, they are still there, they are just blocked. They are not allowing any user data to go in or out of that port. But the bridge protocol data unit, they are allowed to go through. So as you can see, I put it in the dotted dashes there because the user data is not allowed, but bridge protocol data unit frames that are used for the spanning tree protocol to prevent loops are allowed. So we still allowing bridge protocol data units to go through. The physical path still exists to prevent redundancy, but these paths are disabled to prevent the loop from occurring. So we still have we are still having these connections, but they are disabled to prevent the loops. If the path is ever needed, the redundant path becomes active. So imagine this path is active at the moment, but it goes away. Then we select a new path to the destination, to the root bridge. So spanning tree protocol introduction. Spanning tree protocol ensures that there is only one logical path between all destinations on the network by intentionally blocking redundant paths that will cause a loop. A port is considered blocked when a user data is prevented from entering or leaving that port. So you have to remember those terms. The port is considered blocked only when it prevents the user data. But remember, bridge protocol data unit, they are still allowed to go through. This does not include, like we said, BPDUs, and the physical paths are still existent to provide redundancy, but these paths are disabled to prevent the loops. If the path is ever needed to compensate for network cable or switch failure, spanning tree protocol will recalculate the paths and unblock the unnecessary port to allow, or unblock the necessary port to allow the redundancy path to become active. So spanning tree protocol often accounts for more than 50% of the configuration, troubleshooting, and maintenance headaches in the real-world campus networks, especially if they are poorly designed. So this topic is very, very important on the real-world networks. As you can see there, is 50% of your work will be dealing around this protocol. Complex protocol that is generally poorly understood. Radia Perlman, as developer of spanning tree protocol, this is the person who has created the spanning tree protocol. So spanning tree is on by default, right? For all the VLANs, spanning tree is on. But by some reason, if you decided to disable the spanning tree, you can do it by saying no spanning tree and then VLAN and then whatever VLAN ID you want to use, VLAN 10, 11 or whatever, no spanning tree. If, for example, you want to re-enable the spanning tree, you type spanning -tree VLAN and then whatever VLAN number. So by default, spanning tree protocol is enabled for every port on the switch. If for some reason spanning tree protocol has been disabled, you can re-enable it. So spanning tree protocol executes an algorithm called a spanning tree algorithm. Spanning tree algorithm chooses a reference point called a root bridge. Then determines the available paths to the reference point. If more than one path exists, the spanning tree algorithm will pick the best path and will block the rest of the paths. A bridge ID, right? So let me just go back a little bit here. I'm going to very quickly look at this here. So we find out the root bridge. Then from the other switches that are called non-root bridges, they will calculate the fastest path towards the root bridge. Every other path they will be on the blocking mode, right? But somehow we need to elect this root bridge. Now root bridge, the way we elect the root bridge is, root bridge, very important, the way we elect it is through a bridge ID. Now what is that bridge ID? Let me look at here now. Bridge ID. A bridge ID is used to identify each bridge switch. Now remember, bridge and switch is exactly the same thing. Before it used to be called bridge because it had only two ports. One to network A, two connecting to network B. From network A it couldn't go to network B if it was necessary to, the packets or the frames. And from the two ports we added more ports, or they added more ports, and now it was called a multi-port bridge. So bridge and switch is exactly the same thing. So the bridge ID is used to determine the center of the network in respect to spanning tree protocol known as the root bridge. So we need to find out one of the switches to be our root bridge. So imagine in our network we have 5 switches and we can elect one of them to be our root bridge. The way we do that by using the bridge ID. The bridge ID is made out of these interesting attributes. So first, bridge ID is made with the bridge priority and the MAC address. So bridge priority is 2 bytes and then the MAC address of 6 bytes. So bridge ID is made out of bridge priority, right? So by default is 32,768 plus the system ID, which is the VLAN number, and then the MAC address, right? Whoever wins, right? So we need to find out who's the root bridge, who's in charge, and so on. To find out whoever is in charge, we look at the bridge priority first. If the bridge priority is the same, then we look at the MAC address. So each switch has a unique bridge ID. Original 802.1d standard, the bridge ID priority field plus MAC address switch. All VLANs were represented by a common spanning tree, one spanning tree for all VLANs. Per VLAN spanning tree requires a separate instance of the spanning tree for each VLAN. So for that reason, we have to add extended system ID. So spanning tree algorithm, how to find out the root bridge. So if we look at this, this is our 3 switches here. We have a switch 1 in the top, 2 and 3. So the first thing that we're going to look is the priority. So the root bridge serves as a reference point for all spanning tree calculation to determine which redundant paths to block. An election process determines which switch becomes the root bridge. So we need to have an election. The bridge ID is made out of a priority value, an extended system ID, which represents the VLAN, what VLANs it belongs, and the MAC address of the switch. After the switch boots, it begins sending out bridge protocol data unit frames every 2 seconds. The bridge protocol data unit contains the switch bridge ID and the root ID. So as soon as the switch boots up, it will send this bridge protocol data unit. That's the language they talk about to find this selection, this root bridge. And in that bridge protocol data unit, they all claim to be the root bridge. As soon as it turns on, it says, yep, I'm the root bridge here. And then, unless someone comes with a better bridge ID, then it's going to end up being the root bridge. We have to have only one root bridge. So there is only one root bridge elected for each spanning tree instance. Right, so if you look at here, like in this section, first thing we're going to look at this bridge priority. So bridge priority, this one has 32.768, this one has 32.768. We're not going to worry about MAC address at all, or what VLANs does it belong and so on. We just look at the bridge ID by looking at the priority first, and we're going to compare the priority. The one with the lowest priority will win the election. and this one here has the lowest priority, and this switch, or switch 1, is a root bridge because it has the lowest priority. It's important that you do change this priority, because by default the priority is 32768, right? That's the default. If you leave it as the default, the switch with the lowest MAC address will win. Everything in the spanning tree, you think lower, it's better, yeah? So bridge priority lower is better. 32768 is worse than 24,577 here. 76, but they added a VLAN, which is VLAN 1. Now, if we leave it to default, they're going to look at the MAC address. The one with the lowest MAC address will win. And the oldest switch that you have on your network has the lowest MAC address, and that's going to win. So we did the election here, and this bridge here, this switch 1, became the root bridge. The port role describes the relation in the network to the root bridge and whether they allow traffic or not. So we have to find out, okay, what's the port roles? So all the port roles, all the root bridge ports are going to be on the forwarding mode, and they're called designated port. All non-root ports that are still permitted to forward traffic on the network, they are called designated port. So for example, all the ports on the root bridge are called designated because they're allowed or they're permitted to send user data. And here, for example, we have a designated port on this port here as well because it's allowed to send user data. Root ports are switch ports closest to the root bridge. So for example, a root port, this is going to be the root port because that's going to be the closest towards the root bridge. Any information I'm going to send to the root bridge, well, something like topology has changed or something, I need to notify my root bridge, and that's going to be the fastest port towards the root bridge. Alternate and backup ports. Alternate ports and backup ports are configured to be in the blocking state to prevent loops. So alternate ports, for example, this is a backup port. So if this link fails, this one link will turn on and whatever. This is called alternate port. But alternate port is not allowed to send the user data, but it's still allowed to send and receive BPDUs. And then we have a disabled port. Disabled port is a switch port that is shut down. So for example, the one important command that we can run in spanning tree is show spanning tree. This is very, very important. Show spanning tree is going to tell you quite a lot of information here. We have, for example, two sections we can see. First, information that we see, well, more than two, but anyway, the first thing we can see, show spanning tree we see here is for VLAN 0001. So we have, this is a spanning tree for VLAN 1. Spanning tree enabled protocol, we can see what protocol we're running. Here is IEEE. Can be any other. We can learn later on, we are learning what kind of spanning tree, different flavors of spanning tree that we have. Here what I need, I'm talking about the two sections. On the top section here, we are talking about the root bridge, and underneath here we're talking about the switch it's on, right? So if I can mark it, it would be nice if I can mark it, highlight, maybe I can. If I do it in red, we do it red. Try this section here. This section is about the root bridge. This section here is about the switch. Sorry, I'm not good at this. This is about the switch that you are running this command at, right? Can I undo? Oh. Okay, fine. I found out how to undo what I did. Anyway, this area here, it's about the root bridge. This area here is about the switch you run in this command. So as you can see here, it says when we run show spanning tree, we look at the MAC address of the switch, which is here. If the MAC address of the switch is exactly the same, and then this is the root bridge. Here is nice, it says this bridge is a root bridge as well, but this MAC address here represents the root bridge MAC address. This MAC address here, it represents the MAC address where you ran this command. So for example, if we ran the same command but now on the switch 3, you can see the show spanning tree command that we ran on switch 3, it doesn't say this is a root bridge. So right away we know that this is not the root bridge. And we can look at the MAC address. MAC address is a bit different, right? Here starts 001, here starts with 003. So we can see the MAC address here is different. So this area here, they can see, it's called the air. All the information here, they can see, is about the root bridge information. All information that you see here is about the switch where you're running this command. So for example, we can see the priority 32769 here. The priority 32769. So the both switches, they have the same priority, 32769, which is 32768 left to the default plus 1 for VLAN 1. So 32769. So priority, you can see here, priority 32768 plus system ID extended is 1, which is VLAN 1. So that's why 32769. So the first thing, there's a tie. We can't find out the root bridge just because of looking at that information. So we have to look at the MAC address. When we compare the MAC address, or like I said, it's better. The root bridge MAC address was lower than our MAC address here when we ran this command. So that's why this is the root bridge. The cost is how much does it cost us to get to the root bridge, which is 19. We're going to find out what is this is based on the bandwidth. And the port that we're going to use to get to the root bridge is fast Ethernet 01. Now hello time is 2 seconds. So the root bridge is going to send us hellos every 2 seconds. Maximum age is 20 seconds and forward delays is 15 seconds. Now these timers here are our timers, but these timers are not valid until the root bridge fails. So we can change the timers here, hellos for example every 10 seconds and so on, but they don't have any meaning they only look, you don't do anything. You are just changing it. The root bridge, the timers are important. Okay, so path cost. When a root bridge has been elected for the spanning tree instance, the spanning tree algorithm starts the process to determine the best path to the root bridge from all destination in the broadcast domain. So for example, imagine that you are not the root bridge. You have 2 links connecting you to the root bridge. You're going to find out which link is the fastest to go to the destination. And we look at the cost there. So for example, if one link is 100 Mbps, that's cost 19. If the second link is 1 Gbps, so the cost is 4. So it's going to choose the fastest, which is lower cost, which is 4. Now before, 10 gig and 1 gig, they equaled 1. So that wasn't very good because there's a massive difference between 1 gig and 10 gig link, yeah? So the revised IEEE specs, these are the costs. Now the 10 gig link is 2, 1 gig link is 4, 100 Mbps is 19, and 10 Mbps is 100, right? These are the old specifications. You don't need to really know about it, but these are the new specifications. So what we use this path cost is to find out which link is going to be our root port. What port I'm going to use to talk to my root bridge. The path information is determined by summing up the individual port costing along the path from the destination to the root bridge. So for example, from me to the root bridge is 19. When I tell my neighbor, the neighbor is going to add the cost from the neighbor to me. So for example, if that's another 4, it's going to add, so the root path cost or root port, the cost is going to be 19 plus 4, which is 23. Note, as the newer faster Ethernet technologies are entered the marketplace, the path cost value may change to accommodate the different speeds available. Although switch ports have default port costs associated with them, the port cost is configurable. So this cost, if you leave it default, fast Ethernet is going to get 19. Gigabit, 1 gig, it's going to get 4, and so on. But you can change them. You can change the way you want it. Like you can make sure that if you want, the fast Ethernet will be more preferred than the gigabit. If you want to change them, now the command is spanning tree cost 25, for example, to increase this cost. Instead of 19, I want to put it 25, right? So roll port decision for rapid spanning tree. In the example, switch 1 is the root bridge. The switch 2 and switch 3 has a root port configured on the port connecting to switch 1. After switch has determined which of its port configured as root port role, it needs to decide whether it has the designated or alternate port. So let me just go back here. Now we have collected this is the root bridge. This switch here and switch here need to find out the root port. What's its fastest way to the root bridge? The path 1 could be, I can go this way, they're all fast Ethernet, or I can go this way. Now this way is 19. So, if I go this way, that's 19, plus another 19, that's 38. So I'm going to choose this thing, yeah, the fastest thing. The root bridge automatically configured on all switch port is designated role. So all the ports on the root bridge are designated. Other switches in the technology or topology configured with the non-root ports are designated or alternate ports. Designated ports are configured for all LAN segments. So every segment is going to have one designated port. So remember, there's like a 3-1 rules in here. We have one root bridge per topology, one designated port, and one root port. So every non-root bridge has one root port, and every segment has one designated port. When two switches are connected to the same LAN segment and root ports have already been defined, the two switches have to decide which port is configured as a designated port and which port will remain an alternate port. So here, this is link, the decision is, we cannot break up the loop here. So they need to find out, okay, well, which one is going to be the designated and which one is going to be alternate. So the way they find out is the switches on the LAN segment exchange the BPDU frames, which contains switch bridge ID. First priority is the lowest path cost to the root bridge. So for example, if this port towards the root bridge, we look at the priority, okay, we look at the speed as well. So for example, first thing that we're going to look is how fast is this port to the root bridge. If it's 4, for example, and this one is 2, well, this one is going to be the designated port. So the first thing that we're going to look is like which one is the fastest. Then we look at the priority of the lowest, if it's equal, then the switch lower bridge ID will be configured as a designated port. For example, if it's 19 for both, is the same fast Ethernet, then we look at the bridge ID. Then we go through the election again. We look at the priority, bridge priority. If it's the same, then we look at the MAC address. This is a bridge protocol data unit frame format. So first we have a different fields on the bridge protocol. The spanning tree algorithm depends on the exchange on the bridge protocol data unit to determine the root bridge. So this is like, it's like a bread and butter of spanning tree. We have to send these VPTUs around, and we're going to find out what's inside there. So the first 4 fields identify the protocol, the version, message type, and the status flag. So here we identify, for example, protocol ID, version, what spanning tree, for example, we are using, what version we are using, what is the message type, is it just a normal BPDU, topology change, and if there's any flags associated with that. The next 4 fields are used to identify the root bridge and the cost to pass the root to the root bridge. So the root ID, so this is the root bridge's ID, because even if we are not the root bridge, we can advertise it for the root bridge, for example, to the next switch. Cost of path, so how much does it cost me to get to the root bridge, the bridge ID, and the port ID. So for example, here we have our bridge ID and the port ID that connects us to the root bridge. And the last 4 fields are all timers fields that determine how frequently BPDU messages are sent and how long the information received through BPDU process it receives. So for example, the message age, max age, hello time, forward delay time, these are the timers that BPDU is going to give. So these are the timers first. So we have a hello time. Hello time, the time between sending of configuration BPDUs to the root bridge. So the root bridge is going to send these BPDUs, right? Everybody should get those BPDUs. So every 2 seconds, the BPDU is going to come from the root bridge. And other bridges, they're just going to relay that BPDU. Forward delay is duration of listening and learning states. So if there's a problem, so we need to elect a new root port or a new root bridge or something, we have to go through this timer, which is first listening. If there's any other better port or better with a better BPDU or whatever, then we have to go through the learning state, which is learning the MAC addresses before we move to the forwarding. And that is by default is 15 seconds. And the time BPDU is stored is called max age time. and that's for 20 seconds. So if I receive a BPDU now, so in the next 2 seconds I expect another BPDU. But if I don't get another BPDU in 2 seconds, how long I'm going to wait for that first BPDU that I received before I make age it, which is 20 seconds. So 10 BPDU if you miss, that's it. So hello time, IEEE specifies the default by 2 seconds. The interval between the configuration BPDU, because there's a configuration BPDU, like normal BPDU, the root bridge sends, and there's a topology notification BPDUs that everybody can send it if there's a change in the topology. The hello time value configured at the root bridge determines the hello time for the non-root bridge switches, which means that you can configure this hello time on any switch that you want, but it will not going to have an effect. Locally configured hello time is used by the topology change notification BPDUs. For example, if the topology change notification happens now you can use your hello time, whatever you have configured. Forward delay time, the default value of forward delay 15 seconds, originally derived assuming a maximum network size of 7 bridges hops, a maximum of 3 lost BPDUs, and hello time interval of 2 seconds. Forward delay is used to determine the length of listening and learning state. And then we have the max age timer. The max age timer is the time that a bridge stores a BPDU before discarding it. Each port saves a copy of the BPDU it has received. If the device sending this best BPDU fails, it may take 20 seconds before a switch transition the connected port to listening mode. So we have these port states. Each layer 2 port on the switch running Spanish tree protocol exists on these 5 port states. So it can be blocking. The layer 2 is a non-designated port and it does not participate in frame forwarding. The port receive BPDU. The port spends 20 seconds in this state max age. So in the blocking mode, the bridge will still receive BPDUs, but it will not send or receive any user data. And then for some reason, if that port has to transition to the forwarding mode, so something has changed, then it's going to go through the listening mode. Listen in Spanish tree has determined that the port can participate in the frame forwarding, user frame forwarding, according to the BPDUs that the switch has received so far. By default, the port spends 15 seconds on the forward delay state, and then we move on to learning state. After listening, we go to learning, and the layer 2 port prepares to participate in frame forwarding and begins to populate the CAM table. By default, the port spends 15 seconds in this state, which is forward delay state. And then we go to forwarding. The layer 2 port is considered a part of the active topology. It forwards the frames and also sends and receives BPDUs. And the last mode, the 5th mode, is called disabled. The layer 2 port does not participate in Spanish tree. So these are your 5 Spanish tree protocol states: blocking, listening, learning, forwarding. Now the important thing is to configure the root bridge. Now you can do the command to configure, to make sure, which you have to do. You really have to configure the root bridge. You don't leave it by default. Spanish tree, VLAN 1, priority, and then give it a priority, whatever priority you want to choose. This command statically configures the priority in multiplies of 4096. So the priority can't go 1, 2, 3, and so on. You can go 0, 1, 4096, and you have to add that 8000 and whatever it's 182, 92. You just put a number, then it'll give you the time. You put a question mark, and it's going to give you the priority multiples that you can enter. Valid values are from 0 to 61,440. Default is 32,768. Lowest values, that will become the root bridge. Or an alternate command, it will be this command will force the bridge to be the root. So Spanish tree VLAN 1 root primary. What this command is going to do is going to find out what is the primary root bridge priority, and is lowered by 4096. The Spanish tree root primary command alters the switch bridge priority to 24576 plus a VLAN ID. If the current root has a bridge priority which is more than 24,576, Then the current is changed to 4096 less than the current root bridge. And then if you want to have like a backup of the root bridge, you create a secondary. This command configures the switch to be the secondary root in the case of the root bridge fails. The spanning tree root secondary command alters the switch bridge priority to 28672. If the root switch fails, the switch becomes the next root. So if the root bridge fails, then this switch with this command will become the next root bridge. I understand this is a massive topic, so you better spend like I'm going to do like about 4 hours in this topic, but that's not even enough to what you have to learn and spend on this topic. Now I'm going to do a demonstration on building a switch network with the redundancy links. So, okay, I'm going to do this lab on packet tracer very quickly, but follow the links if you want to see the whole lab done in the real devices. Okay, so open the packet tracer. Not that. Okay, now the packet tracer is open. So what I'm gonna do is I'm just gonna grab 3 switches, 2960s. So I'm gonna delete that switch 0. So switch 1, like we had before, switch 2, and switch 3. Let me delete this switch 0. I'm gonna connect my switches with a crossover cable. So switch 1, fast Ethernet 01. It's gonna connect with fast Ethernet 01 or switch 2. And fast Ethernet 02 to fast Ethernet 02, and then switch 1 is going to connect with gigabit Ethernet 01 with the switch 3 gigabit 0 Ethernet 01, and then switch 1 gigabit 0 Ethernet 2 with gigabit 0 Ethernet 2 or switch 3. Switch 2 and switch 3, they're going to connect with 10 and 11. So 10 on switch 2, 10 on switch 3, and 11 on switch 2. Oops, sorry, I think 11. I think I clicked 9. So 11 with 11. And let me just get rid of the lights. Okay, there we go. Right, so these switches, they're going to go through the election and find out which switch is going to be the root bridge. So if I open the switch 1, for example, click on switch 1, CLI, and the command really is to see enable. Let's give a name, config t hostname SW1, and let's give all. Go to switch 2. Just give a name. So enable config t hostname SW2, and switch 3. I want to do it fast because I don't want you to spend too much time here. If you want to do the whole lab, you can just follow the link. SW3, this one here. So we have SW2 here and SW1. That's from our lab. So when I do show spanning tree VLAN 1. Now let me just expand this a little bit so you can see it better. Here, so we can see the spanning tree for VLAN 1. So VLAN 1 there. The default spanning tree is IEEE, and the priority is 32769. Now it doesn't say here this is the root bridge anywhere, so I know right away that this is not my root bridge. This switch that I've run this command, which is switch 1, is not the root bridge. This information here is about the root bridge information. It's about the bridge. Sorry, it's about the bridge that you run this command information. This information here is the root bridge information, right? So that's why I have two MAC addresses. So when I compare this MAC address to this MAC address, I can see it's different. So this is my MAC address, or switch 1 MAC address, which is 00D0, and the root bridge MAC address is started with 001. So that's not my, that is a root bridge. That's why I lost this election, or switch 1 lost the election. The port, the cost is 19 towards the root bridge, right? So that really tells me right away that it's a fast Ethernet link. Because if it said 4, then I know that, okay, it's towards the switch 3. Remember, I put the gigabit interfaces towards the switch 3. So switch 2, I'm assuming this is my root bridge. Anyway, so if I go to the switch 3, for example, and show spanning tree VLAN 1, right? Here, expand a little bit. It's not the root bridge either, because it doesn't say that, right? The priority is the same, but you can see the MAC address has got a higher MAC address than the root bridge. So this switch 2 here is the root bridge. Let me just maximize a little bit. Let me expand it here. And show spanning tree VLAN 1. So here this switch says this bridge is the root bridge. And this is my priority. 32769, which is the same with everybody else. We left the default. We didn't change anything. We just grabbed those switches and brand new switches. But the reason why you won the root bridge is because it's got the lowest MAC address. As you can see, all the ports are in designated mode, right? And forwarded, which means that they are forwarding user traffic as well as BPDU. The cost is 19, which is everywhere without all the switches as fast Ethernet connection. Now this is switch 1. It needs to find out what port is going to be the port that connects the fastest port towards the root bridge. And the fastest port, that's called a root port. So it chose port 1, FA01, to be the root port, right? FA02 now is on blocking, because if that would be forwarding as well, then there will be a loop. Right? So one port, one of them is blocking. Now, he has chosen for other two ports connected with the gigabit towards the switch 3 as a forwarding mode. Right? So they ran another election and they found out, okay, well, this switch is better than the other switch 3. That's why they are forwarding. Switch 3 has chosen the FA010 to be in forwarding mode, and all other ports are in blocking mode. Why this G01 and 02 lost is because they went through another election, right? So when we look at this MAC addresses again, the port is the same, but the MAC address is not the same. You can see 00D0 and this one is 00E0. Since this one's got a lower MAC address than this, that's why we won the election. So A, B, C, D, E, so D is lower than E, yeah? That's why we won the election, and thus for those two ports. And that's why they are forwarding mode, right? Now you can see the cost is 4 because we chose a gigabit link towards between switch 2 and switch 3. The root bridge is 19 towards the root port, root port towards the root bridge is FA01 and the cost is 19, it's fast Ethernet. Now the other port is blocked, right? It's all the same now, but it came down to what port has got a lower number. So FA01, just because it's 01, is the root port instead of FA02. Everything else was the same. Right, so if we want to make this bridge to be our root bridge, we will go to the config mode and say spanning tree, VLAN 1, primary, root, primary. And then I'll go to switch, for example, 3 to be my secondary. So config T, spanning tree, VLAN 1, root, secondary. Root, secondary. So now, when I run the command, the same command, show spanning tree VLAN 1. See, this command, this has been learning. Just cache it to be the learning. But this is the root bridge now, right? Because it's got a low priority. right? Now if I go to switch 2, well, I haven't changed anything here. So show spanning tree VLAN 1. You can see the information on the top here is about the root bridge now. It doesn't say this is the root bridge. It did say before. So if you look before, it said this is the root bridge before, but now it doesn't say this is the root bridge. It says the priority of the root bridge is 24.577. So 24.576 plus 1 should be that 1. My priority is 32.768. That's why I lost. All my ports are in blocking apart from the root port. The root port, which is FA01. Okay, so we do the same command in the show spanning tree VLAN 1 for switch 3. And you can see that it says my priority is 28.763, but I still lost because I got better priority. The root bridge has got better priority than me. The root port is my gigabit port. So cost of 4. Right? That's the cost for root port. Okay. And forwarding is G01. So they went to election between those two. And again, there's nothing separating between them. So G01 has won it because it's lower port than G02. Okay. This has been Krasny Krasnichi. I've been talking to you about first section. This is divided on 4 sections. So we still have to go through section 2.2, varieties of spanning tree protocol. But this is like the foundation to the spanning tree, which you need to know, the section 2.1. Thank you very much for watching. You have been Rasar. Have a good day. Bye bye.